Hello students, in this video we are going to study magnetic field due to a long straight current carrying conductor. So basically we are going to take a long straight current carrying conductor and we'll find the magnetic field around that conductor. We'll try to find the magnitude as well as direction of a magnetic field that is set up around that straight current carrying conductor. So let's begin the process. Here we consider a straight conductor XY as I am showing in the diagram. I have considered a straight conductor XY carrying a current capital I from point X to point Y. Now we want to find its magnetic field at some point. Let that point be capital P here. So here's the point P where we want to find the magnetic field because of this conductor, and the distance, or I can say the perpendicular distance of this point P from the conductor or from the wire is small a. Let this distance be small a and named it as PQ. Now PQ is the distance of point P from the wire XY, and this distance is equal to A. Now to apply Biot-Savart law, we have to consider a small current element dl vector at a point O on this wire. So here I am considering, this is the small current element because of which we are first calculating the magnetic field. So this is like this. This is the dl vector current element at point O. I'll name this point as O, and the distance of this current element from the observation point where we want to find the magnetic field is R vector, or we can say the position vector of this point P with respect to the current element is R vector, and the angle that this current element makes with position vector R vector is theta. Theta is the angle between dl vector and R vector. Also we assume that the distance of this current element from point Q is small l. Small l is the distance of this current element or the point O from the point or the center of the wire, that is Q is small l. So now after assuming all these factors, we can find the magnitude of magnetic field dB vector because of this current element at point P using Biot-Savart law. So what we are going to do, first we write what we assumed. First we've assumed a wire XY, then a current I flowing from X to Y. Then we assume that the observation point where we want to find the magnetic field is capital P. Then we consider a current element at O dl vector, and distance of this current element from Q is L. Also perpendicular distance of point P from conductor XY is small a. So these are all the assumptions that we assume to find a magnetic field at point P. Now we can apply Biot-Savart law. Then according to Biot-Savart law, we are going to find the magnetic field strength at point P because of the current element dl vector. Then according to the law, we get dB is equal to mu naught upon 4 pi I dl sine theta upon r square, where theta is the angle between dl vector and r vector. This is the angle between current element and the position vector r vector. So this we get from Biot-Savart law. Now in the right angle triangle OQP, let's see the right angle triangle OQP, 90 degree is that angle, is the angle PQO. So in triangle OQP, what we have, angle OQP is equal to 90 degree, right? The one more thing that we should assume that this is the whole length of the conductor. So we want to find the magnetic field because of this whole length. Right now we are finding for this current element, and then we will integrate it for the whole length. So we will integrate this for the whole length. For that we need the angle that these points x and y makes at observation point P. So let the angle that point x and point y make at observation point P are phi 1 and phi 2, means this angle is phi 1 and this is phi 2. So if we want to find the angular separation, or we are considering the angular separation of these points x and y, so we denote it by phi 1 and phi 2. Also for the current element, this for the current element, the value of the angle is phi. Now come back to our calculation. In triangle OQP, what we have is theta plus phi is equal to 90 degree. Because this is 90, so the remaining two will form combinedly 90, or theta is equal to 90 minus phi, right? Because of this, sine theta is equal to sine 90 minus phi or cos phi. That means sine theta is equal to cos phi. So now what is our target is, in this relation we want to eliminate the term theta first thing. So we want this formula, this whole formula in terms of phi. So we want to eliminate r, dl and sine theta, and want their values in terms of phi. So first of all I get the value of sine theta in terms of phi, that is cos phi. Now the next thing that I am going to find is r. So from the triangle OQP, cos phi is equal to, now cos phi according to trigonometric relation, cos is equal to होता है base upon hypotenuse. So for phi, base is a and hypotenuse is r. Cos phi is equal to a upon r. It implies r is equal to a upon cos phi, or I can write it as a sec phi, equation number 2. So the next thing, that is r, I also find r in terms of phi. Now the last thing is dl. Now I want to find dl in terms of phi. For this I am going to calculate tan phi from the triangle OQP. So from the triangle OQP, tan phi is equal to, now tan phi is equal to होता है perpendicular upon base. Now this perpendicular for phi is L and base is A. So tan phi is equal to L upon A, or L is equal to हो गया A tan phi. But our task was to find dl instead of L. So we will differentiate this equation, and on differentiating this we get dl is equal to A sec square phi d phi, equation number 3rd. Now from 1, 2 and 3 we are going to substitute these values in the term dB here in Biot-Savart law. So from 1, 2 and 3 we substitute values in Biot-Savart law, right? So then we get dB is equal to mu naught upon 4 pi as it is, I as it is. In place of dl I am writing a sec square phi d phi I dl, एंड साइन थीटा की जगह मैं लिख रही हूँ कॉस फाई अपॉन आर स्क्वायर के रिप्लेस करके आ जाएगा ए सेक फाई का होल स्क्वायर. On solving this we get mu naught I upon 4 pi sec square phi cancel, a से एक a cancel हो जाएगा, then it will be 4 pi a denominator में and numerator will be cos phi d phi. So this is the value of dB that we get in terms of phi. dB is equal to mu naught I upon 4 pi a cos phi d phi. Now this is the value because of the current element that we have considered at point O. Now if I want to find the magnetic field because of the whole conductor, then I have to integrate this in terms of phi or in limits of phi. So for whole conductor the angle phi varies from phi 1 to phi 2, but phi 1 is along the negative axis and phi 2 is along the positive axis. So limits will vary from minus phi 1 to plus phi 2 for this whole wire xy. So now the value for whole conductor means the total field capital B vector, this is the magnetic field at point P due to the entire conductor xy, which is obtained by integrating dB. Now here I am first finding the magnitude, integrating dB within the limits of phi, that is minus phi 1 to plus phi 2, right? So let's calculate this. When we substitute the value of dB, what we get, mu naught I upon 4 pi a are constants. So ये सब integral के बाहर हम ला सकते हैं and we have to integrate cos phi in limits of minus phi 1 to plus phi 2. On solving this we get mu naught I upon 4 pi a and integral of cos phi is sin phi, and we have to put the limits minus phi 1 to plus phi 2. On substituting this we get the answer. So the answer we get is mu naught I upon 4 pi a sin phi 2 minus sin minus phi 1. But the property of sine is that sine minus theta is equal to minus sine theta. So we can write it as minus sine phi, and this minus sine phi and minus will become plus sine phi. So the final answer of capital B that we get is mu naught I upon 4 pi a sine phi 1 plus sine phi 2. This is the value of magnetic field strength at point P. Now the next thing is the direction. As we know that magnetic field is a vector quantity, so we want its magnitude as well as direction both. Now to find the direction we will use a right hand rule that we have studied in our previous video. So according to right hand rule, what we did, we hold the conductor from our right hand such that the thumb of the right hand points towards the current flowing in the conductor and the direction of the curl of our fingers of right hand gives the direction of magnetic field. So let's see the diagram. The diagram we have is like this, like we have a conductor xy and current was flowing like this. So if I hold this conductor from the right hand such that current points in the direction of thumb, so it's like this. If current is flowing from x to y like this and I hold it from my right hand such that thumb points in the direction of current, and this is the direction of the magnetic field, means the direction of my fingers curling across this pen or the conductor gives the direction of magnetic field at the observation point. So observation point is somewhere here P, and we hold it like this, it's like this, right? So the fingers are going inside the paper. That means the magnetic field lines around the conductor are in the form of concentric circles, like this. These are in the form of concentric circles around that conductor, and the direction that we are taking is anti-clockwise or clockwise, depends on the flow of current. So in this case the direction will be like this, like we are going like this, then we can plot the direction in this manner. When current is flowing towards upwards, then it's going like this, we are going from here to here, from right to left. So this is the anti-clockwise way of direction. This is the direction of anti-clockwise sense, means if current flows upwards, then the line of force or the magnetic field lines have anti-clockwise sense, while if the case was opposite, if current was flowing, I am just considering, if current was flowing downwards or like this from y to x, then I have to hold this wire in this motion. This is the direction of current. if अगर हम ऐसा एग्जाम्पल लें कि आपका जो करंट है वो y to x फ्लो करता है, then I have to point my thumb towards y to from y to x, and at that time the fingers will go inside from left and come out from right, means like this kind of motion. Then such type of motion, when we plot, it gives the clockwise sense of direction. So if the current flows downwards, the magnetic lines of force have clockwise sense, while in upwards they shows anti-clockwise sense. So in our case what we considered was upward motion of the current. So at point P the direction of current will be in anti-clockwise, the direction of magnetic field lines will be in anti-clockwise sense, right? So it is like this. If we talk about, if we take this conductor in the plane of paper, then the magnetic field lines are perpendicular to the plane of paper and going inwards at point P, right? And the direction that we show here at point P, the direction of magnetic field is normal to the paper and into the plane of paper, that we show by a cross, right? So the direction of magnetic field at point P is normally into the plane of paper, and the strength of magnetic field is capital B is equal to mu naught I upon 4 pi a sin phi 1 plus sin phi 2, normally means perpendicularly into the plane of paper. This is the value of magnetic field, means this will show the strength, and this is the direction is the of the magnetic field at point P near a straight current carrying conductor. So this was all about this video, and in the coming video we will be seeing the magnetic field due to circular conductors. Okay, so till then stay tuned and keep studying. Thank you.